you. So yeah, I'll give you guys a little bit of discussion today about life after grad school. So let's see, where's the all right, where's you got a clicker? Haha. Space bar's not going
Okay, yeah, I can use.
down. Okay, up and down arrow keys. Gotcha. Okay. Okay, so today I'll a brief outline. I'll give you some discussion about my academic and professional histories, kind of what I do for a living as the technical director at Santa Barbara Infrared. Some discussion about how to apply some of the things that I learned here in school as to working in industrial settings. A few more specific examples from my experience, and then some parting thoughts about my take as a physicist in industry and some reflections on the life part of the life after grad school. So I got my bachelor's degree in aerospace engineering in 1991 from here at University of Florida. 1991 was not a great time to graduate as a aerospace engineer. There were companies called McDonnell Douglas that you may have never heard of because you're too young. Or you probably heard of Lockheed Martin. The Martin part was from Martin Marietta. These companies, like those, Grumman, they laid off tens of thousands of engineers right about the same time I graduated. And so there was no chance whatsoever for me to get a job. So I spent a year working as a draftsman at a stainless steel pipe plant not far from where I lived, and decided that I didn't really want to be a draftsman for the rest of my life, and went back to school studying physics in 1992. The nice thing about physics, okay, the funding in physics is low for the graduate students, but it's constant. It doesn't go up and down like some of the other things do. So if you could get in, you could finish. So that's what I did. Back to school in physics. Got my PhD in 1999 studying time-resolved infrared spectroscopy under Dr. Tanner. So my professional career. So one thing, if you guys don't know, if you're not in academia, there are not that many jobs out there that say physicist on them. So I spent about 6 months looking for a job with no luck whatsoever. And then a retired engineer from NASA came to the lab, wanted to measure a few things. I offered to help him. Was here for 2 or 3 days and got to know him. And he's like, you know, hey, there are these 2 companies that I know of that are looking for engineers. Why don't you give them a call? So I did, talk to them. Both of them offered me jobs. And I, after flying around the country to interview with them, and I ended up taking the one in Santa Barbara over the one in Hartford, Connecticut. My wife is from Taiwan and she really doesn't like cold weather. So she's like, we're going to Santa Barbara. Okay, fine. Go to Santa Barbara. So I went to Santa Barbara, worked for a small company called Spectier. I was a system engineer working on hyperspectral imagers for and polarimeters for remote sensing application. These are airborne instruments that you put in a plane and go fly over things to do imaging spectroscopy. The picture on the right is the hyperspectr. This is like some great big box that we'd put in an airplane with a hole in it and fly over things. This is an example of the imagery that we collected. This is cold oil point. This is a false color image with the red being just past the chlorophyll edge, a little bit longer than actual visible red light, so that all the vegetation shows up red. And I don't know if you can see it on here. You probably can't, but there, you can actually even see some of the kelp that's up close to the surface. You can see through things. So these are imaging spectrometers used to fly over things to do things like plant studies, mineral studies. People use them to find gold and oil and to find plants that are stressed because they've got some disease or there's been some infestation of some insect or something like that. So continue on Spectre. This is easily my most fulfilling job that I had since I've left school. Involved all aspects of hyperspectral imaging. I got to do instrument design. I got to fly with the instrument. I was an aerospace engineer. I love to fly. Maybe not every day, but getting the chance to get up there and fly. Flew across the country twice in some small plane. It was loads of fun. The pilot let me fly the plane sometimes. It was truly, truly awesome. I went through and did calibration. I did data analysis. I did data products. I touched like all portions of this field of hyperspectral imaging, and it was really fantastic. So then you should ask, why don't you still work there? And the answer is, Spectre had a management change. They shifted their focus from doing instrument design and other things that I was really interested in to just doing flight operations. And they moved from Santa Barbara to Reno. So the design office in Santa Barbara was closed. They offered me to come out to Reno, but they offered me to a lower pay to reflect the lower cost of living in Reno too. So here, come do this thing you don't want to do for less money in a place that you don't want to live. I politely declined. A week later, I started at Santa Barbara Infrared. So this is it's a HICO. You can tell they're a HICO company. It's a subsidiary of HICO, but the actual SBIR office is fairly small. It's only got about 80 people. I've been working there since 2004. SBIR focuses on infrared test equipment, things like blackbodies, target projectors, laser rangefinder testers, and dynamic infrared scene projectors. So I started as the system engineer for the large format resistive array, the LIFRA program. It's a 1024 by 1024 infrared scene projector. About a year later, I got promoted to the system engineering manager for all the RSP group. Basically, I did the exact same thing I was doing, except as manager, I had to give people reviews and I had to go through piles of training on what not to do while I was at work. So mostly the same, but things that weren't that much fun to do. A few years later, I got promoted to technical director. This basically made me responsible for all the technical side of all SBIR products, not just scene projection. And I was still managing the IRSP group. About 10 years later, one of the SEs that I hired into the group said he wanted to become a manager. So we let him. And he took over the group, and I have not managed people ever since. And I am happy that I have not managed people ever since. So what does technical director mean? My duties are basically, I'm the principal investigator for all of the scene projection research projects. I'm the product expert, meaning, if somebody has a problem with some product, for most of the standard products, they come to me to ask them about them. I talk to customers and other engineers about infrared and visible radiometry. I am the troubleshooter of last resort. Basically, when people run out of ideas of things because things don't work, they come to me. And then I'm also the system engineering lead for about half of the R&D that's not scene projection related. So the things that take most of my time, scene projection, black bodies take up the vast majority of the two products, and troubleshooting is a non-trivial amount of my time. When things go wrong, and things do go wrong, I spend a lot of my time trying to figure out what went wrong and how to fix it. So a little bit more about black bodies. They're basically, this is a black body. It's a uniform controlled infrared source, provides a known radiance for people that need it, provides a nice uniform plate. This one's about 4 inches square, very uniform. People use them to do non-uniformity calibrations on cameras. They also use them to back illuminate a target projector. If you want to do like a static test of something, some optic or something like that, they'll put the black body behind a target. Applications include production, where they'll use them to do production non-uniformity corrections for cameras that are going in cars to do collision avoidance. This is a fairly common thing now with the microbolometer cameras they put in they used to have them in Teslas in the very first Model S's with a little camera to look for people and slam on the brakes if they see one. There's lab use where they use them to do radiometric calibration. Field uses include, they'll put them in a target projector to test night vision goggles right before somebody goes out on a mission, or to test the night vision goggles at a depot that have failed to figure out what's wrong and make sure they're working after they fixed them. So just a big aside, it's like a black body, like, what's the big deal? It's a painted metal plate. Okay, that's true. It sounds easy. Making one's actually kind of a pain. Customers ask for millikelvin scale accuracy. They want stability of a millikelvin or less generally, especially around room temperature, which can be quite challenging in an uncontrolled environment. You put it in a lab and the air conditioner's blowing and things are moving around, and you're trying to hold this piece of copper to 1,000th of a degree, and it is challenging. It's a little harder than just a plate with a heater on it. And then there are other more exciting environments, such as being in an airplane or something like that. Typically, they do thousands of cycles. So it sounds simple, but it's actually fairly complicated. So the other thing that takes a lot of my time is infrared scene projectors. So This is effectively an IRTV for testing infrared imagers using a physics-based simulation. So this is like a video game for a missile, is basically what it is. People will put together one of these IRSPs up here in conjunction. We put this on the back end of a collimator. They take one of these things and mount it onto this thing called a flight motion simulator. This is a small one, by the way. The ones that they put our stuff on are even bigger, but I couldn't find a big picture of the big one with a person next to it to show you how big they are. One of these things would easily fill half this room. They're humongous. They're terrifying to watch because they will take, in some instances, 2 scene projectors with a giant optic that weighs 400 or 500 pounds, and it'll go from here to here in about a second and kill you if you're in the room with it. So fairly exciting to watch. They're used for missile testers. So basically what they'll do is they'll take and put a missile guidance system on this inner gimbal here. And then they instrument out what the guidance system is telling the missile to do. So, you know, what it's telling the fins and things on the missile to move. Then it's got a simulation that takes all those inputs and runs a scenario where it's taking the feedback from the missile and feeding it back into the simulation. So the job of the gimbal, the inner gimbal, is to see that the missile guidance system sees all the forces it would in actual flight. So it's getting swung around like it would be in actual flight. And the job of this outer arm, this outer gimbal, is to keep the optic and the IRSP, this hundreds of pounds of stuff, wherever the missile's pointing. So the missile's moving around like this, and the outer arm is keeping up with everywhere it's going. As the missile's going around. That's the job of the IRSP. This whole thing gets simulation control computer, takes the output from the missile, feeds it back into the arm, feeds it back into the IRSP, and it forms a closed loop simulation that allows you to test the missile with actual missile hardware. So you may ask why you should care. And the answer is you should care as a taxpayer. Because it is way cheaper to test a missile with one of these than it is to go out and shoot a missile at a plane every time you want to run a test. Those are very expensive because you shoot the missile, you shoot the plane, you've got all the people that got to go and watch it. And most importantly, those are actually not the biggest reason. The most important is it's much less embarrassing if you miss. So if you shoot the missile and you miss while the senator is watching, your program gets cut. So people do hundreds and hundreds of hours of simulations with one of these before they ever see a flight test. Excuse me. So how to apply my PhD in an industrial setting. You might think that these things are like very different from industrial settings. On the one hand, I'm working with, painted metal plates. And on the other hand, I'm working with, infrared televisions. What does that have to do with academia? Well, actually, I routinely apply all the skills that I learned in grad school on my job. So we do high-level design and analysis. This is part of the job. We do performance calculations. You do order of magnitude estimates to make sure that something you're doing makes sense, that you're actually going to be able to get the amount of signal that you need from the source that you want. You do reviews of specifications. Excuse me. To make sure the things you're going to buy to work on your experiments are going to meet the requirements. It's all pretty straightforward. Troubleshooting is also similar. I'm sure people that are experimentalists, things don't work in the lab, and you got to go figure out why they don't work and fix it. You have to answer questions. Do you have data that's consistent? And if not, how do you get it? You have enough data to be able to know what you're doing or not, or to have a statistically significant sample so that you can believe it. Or my favorite, if it used to work, what changed? People will come to me and say it doesn't work anymore. And it used to work. And Okay, what'd you do different? And oh, well, I changed this, but that shouldn't make any difference. Okay, it shouldn't make any difference, but you changed that. Go change it back and see if it works again. Come on. So, so this thing consistency is something I really want to point out, right? Because I don't understand it, but other people are not offended by inconsistency. We as physicists are, right? I mean, it has to be consistent or it's wrong, right? Your theory has to be consistent. Your experiment has to be consistent, or there's something wrong with it. And the other engineers and stuff don't think that way, and I don't understand why. So this is probably what separates me, or in this case, us, the physicists, from all the other engineering disciplines, or they may not, they don't seem to care. The software guys, like, what's a mechanical engineering problem? I don't understand that stuff, whatever. The ME is like, it's an electronics problem. The electronics guy is, that's a mechanical problem or something else. And they don't see, they don't seem to get this idea that everything has to be consistent. There should be a reason. If something doesn't work, there should be a reason. If there's something physical, it should make sense to you as a physicist. And if it doesn't, something is wrong and you need to go figure it out. The last thing is things like data analysis. You do error estimates, you do figure out outlying points, you fit curves. It's all the same stuff. It's all the same kind of things that you guys have done in grad school. You just do more. So with respect to that, physicists in this kind of setting have an edge. We know something about everything, right? We're physicists. We don't like self-confidence, right? Yes, right. We know it all because everything's about physics. So we know it all. We like to question things. Is your data, what did you do the last time? I don't believe you did that right. I don't think you clicked the button right. Go click it again. So ask a lot of questions. Don't question the company president too often, right? We hate inconsistency, and back to the consistency thing. But it's like, really, most of my troubleshooting comes down to something like this. If somebody else hasn't been able to figure out what's wrong, it's because there's something inconsistent in the data and they haven't seen it. Many issues that are really hard to troubleshoot are because there's not one thing wrong. There's 2 or 3 things wrong. And if you look at the data and you start going through, you say, wait a minute, this data is not consistent with any one thing being broken. It's more than one thing being broken. And recognizing that and then being able to go out and ask what other data you need to collect is very important to problem solving. So as a quick example, recently we had to do calibration verification of a target projector. It's a collimator. Basically, it's a target projector. It's like a collimator with a target and a source. So there are 4 things that matter, right? The collimator transmission, the blackbody emissivity, the blackbody temperature, and the target temperature. Those are the 4 things that you need to do the calibration. So the guys go through and they run their calibration verification test, and what do you know? It matches at -10, it matches at 45, fails at 10. And they come to me, nothing makes sense. I don't understand why. We run the test, plenty of times. We run the test 5 or 10 times. Every time we run it, +10 fails. We don't understand why. So what do you ask? Well, what happens in between, right? Well, we don't know. Okay, go collect more data, right? I'm known for saying go collect more data. Like, you won't believe. People joke about me asking for them to collect more data anytime they come to ask me for a problem, to solve a problem. So they go and collect more data, and this is the curve it follows. So what happens? There's 2 things wrong. Number 1, the collimator transmission is wrong, and the target wheel temperature is wrong. Okay, and you can't tell that without having more data than just the 3 points. You got to calculate it in between. So what was wrong with the collimator transmission? We were using the manufacturer's transmission taken from a test coupon, not the actual measured through the collimator. So should have been okay. And when they did their quick test, it looked okay. So they believed it, but it wasn't right. The target wheel temperature, we're really good at measuring temperature. What happened? New collimator design. The black body was above the target wheel. So when the black body gets hot, hot air rises, the hot air collects up around the black body, everything's fine. The black body gets cold, cold air falls. Cold air fell down onto the collimator. And the temperature sensor on the target is not sitting on the target, it's inboard of the target. So the cold air would fall down and cool half the target wheel, but not the other half, which is covered up. So you get a gradient across the target wheel. So the temperature was measuring the temperature correctly where it was, but that's not actually the temperature of the target. So the slope was wrong, the offset was wrong, makes 2 points look right, but they're both wrong. But the actual calibration was all wrong. So, by the way, we fixed it. Put a fan inside to blow the air off the collimator over the target wheel to circulate the air when it goes cold to make the to make the temperature more uniform. So now I'll talk a little bit about a specific example. This is something I've done sort of as a physicist in industry. So this is actually gave a talk on this at the SBIR conference last April at Defense and Security in Orlando. In Orlando. So this is black body spectroradiometric calibration. So what's going on now is people make better and better infrared cameras. And as they get more sensitive, people want to do more and more and more sensitive tests to test them and to make sure they're accurate. So absolute thermometric calibration with sort of millikelvin scale accuracy that people want is pretty simple. It's not too hard to do a thermometric measurement with probes, or you can get SBRTs or thermistors that are accurate to a few millikelvin, absolute, without too much trouble. Radiometric calibration with a similar accuracy is actually quite difficult, and is becoming more and more common as a request from our customers. So we, SBIR, decided to develop an in-house radiometric calibration capability. Now, you might ask, why on earth do we do this? Because there are commercial radiometric calibration capabilities out there. Well, the answer is expense and time. A spectroradiometric calibration of a black body, if I send my black body off to NIST to get a calibration, costs $25,000 to get a piece of paper that gives me a radiometric calibration to plus or minus like 1%. And it takes them about 6 months to turn it around. Okay? We have a program that requires 50 deliverables that be calibrated. So 50 deliverables calibrated, $25,000, $1.2 million just for calibration, and years of cumulative delay if I had to send those things off one at a time. Oh my goodness, it'd take forever. We'd never get them back. And there's no way my company is paying $1.2 million for calibration. So we figure out a way to do it ourselves. So I have to have one slide at least with equations on it because I'm in physics. There we go. So calibration. You want to calibrate a black body, what do you need? You want to know what the radiance is coming off the black body, and it's basically the emissivity times the temperature of the black body, plus 1 minus the emissivity times the radiance falling on the black body. Really simple. The three main things you need to do to do the calibration: you need the temperature of the source, you need the emissivity of the source, and you need the radiance falling on from the ambient environment falling on the source. So why is this such a pain? Well, one, you need to be a practical calibration. So it needs to provide you calibrated radiance over more than just one temperature and more than just one source temperature, more than just one ambient temperature. Somebody's going to take this thing, go put it in a lab somewhere. The lab temperature, you're not going to know what it's going to be. And you can't just calibrate at one temperature on the black body because they run the black bodies to a huge range of temperatures. So I kind of cheated on my last slide because what you need are the surface temperature of the source, and you need the emissivity of the surface of the source and the ambient radiance. And it's that surface temperature that's a pain, right? Why is that hard? Because nobody measures the temperature of the surface, right? It's really hard to actually do that. Like to put down something and measure the temperature of the surface without touch the surface without screwing something up or having the thing that you're trying to measure in the way is really challenging. So nobody does it. What do? You put the temperature probe inside something, inside the big metal plate that you're going to measure in the black body, but now you're measuring the center of the plate, not the surface. So what happens is this temperature measure is the well temperature, and there's a gradient between that and what the actual temperature of the surface is, right? The room's cooler, the temperature of the surface is going to be a little cooler than what you measure in the well. So then the other thing is, why is the emissivity challenging? Well, you're trying to calibrate the emissivity, and the way you do that is you figure out what the temperature of the surface is. And so if you don't know the temperature of the surface, then you can't do a good emissivity calibration, right? It's like a chicken and egg problem. You need the surface temperature to be able to figure anything out. So what's the solution? So something that more closely related to the actual physical process is go figure out what the gradient is, right? That's what you want to do. You measure this temperature, you kind of know what the temperature of the outside air is. So if you can do that, you can figure out what the, some better estimate of what the surface temperature is, and then use that. So how do you determine the surface temperature? You use spectroradiometric measurements to do that, because it's a Planck curve, right? So you get the Planck up and down, and once you go over the hump of the Planck curve, the radiance with temperature changes very, very rapidly. So at short wavelengths, you get a humongous change in spectrum, in radiance, and you can use that to figure out what the surface is. Now, the way we cheat with that is like we're calibrating black bodies, right? It's not like we're measuring rabbits or unicorns. It's a black body. It's a thing with black paint. So, or some other very black coating. So you kind of know what the reference, you kind of know what the reflectance of the thing is, and you kind of know what the emissivity is, at least a close estimate. So you start with that, you fit it, you adjust the gradient to fit existing emissivity data that you've taken from reflectance or something that you knew about the paint and not just this one particular source that you're looking at. And you turn the knob until you get a good fit. Then you extract the gradient and then calculate the expected surface temperature, and then go through and do the full spectral emissivity from the data that you've got. So how well does that work? Oh, and then also, and then you do that at multiple temperatures to make sure that you've got that this calibration that you're trying to do to cover multiple temperatures is a good single calibration that's consistent across everything. So the setup we used, we have a Bruker FTR. Bruker is the best. Have the unit under test and the reference source on a stage that's all automated. The thing moves back and forth between the source and the reference. We basically do a whole bunch of measurements where we do the source at a high temperature and then move this other source in a low temperature and then switch back and forth. So we're doing lots of differential measurements, and you back and forth so that you track the drift that's going to happen in the lab, because our lab is not some super fancy temperature controlled lab. So we do these things to track drift with the spectrometer and with the lab, so that we average over many hours, so that we average over things like air conditional cycling and things like that to get and to beat the noise down, so we get good data. So here's an example of the results. This the squares here, that is Vantablack. It's like a carbon nanotube based coating with a very, very high emissivity, like almost 1 at short wavelengths, and down to something like 0.5% or so reflectance in the longer wavelengths. And if we use a gradient of about 1% on this, then you can see that all the emissivities line up for all the different temperatures, and you get really nice, a really nice curve. So yay, spectral emissivity works, our gradient works. It's a good idea. Why not just use the well temperature, you might ask? It's not why fool with the gradient? Because of this, right? So this is if we did away with this and did all the fits just with the well temperature. And what you see is it's nowhere close to this, number one, because this is now effective emissivity, not actual emissivity, because you're taking the temperature change into account. And you also see they're not the same. So if I tried to do my calibration down here at 175, where it's hot and I've got lots of data at the short wavelengths, then if I were to actually use that at a lower temperature, then it's actually you actually get a bad calibration, and you can be off by several percent. And our customers are looking for usually something like a 1% or less error total with everything. So we try to keep the radiometric calibration to within 0.5% or less. So now another system or another field that I work on is scene projection. So the whole point of the RSP is to produce a dynamic scene. It's like the infrared television that we talked about earlier. The ones we make at SBIR use a resistive pixel array. It's like 1 million resistors in a square of about 2 inches on the side. And you change the amount of current through the resistors and they heat up and cool off. Pretty straightforward. The trick is customers want the perfect reproduction of reality. They ask for it all the time, and it's really challenging. They want to produce a scene where you can go look at something where you've got the sky, which is cold, you've got the earth, which is kind of warm, and you've got the thing that you're shooting at, which is flaming hot, and they want all that all at the same time on this projector. You know, all displayed all at the same time with really high resolution. They want the projectors to be faster than the imagers. The imagers are now running at hundreds of hertz, and they typically want the projector to be twice as fast. So if you got a 200 hertz imager, they want a 400 hertz scene projector. If you got a 512 by 512 imager, they want a 1K by 1K scene projector. And if you got a 1K by 1K imager, oh, we want a 4K by 4K projector, like, or 2K by 2K projector with 4 million pixels. So our job is to make a device that has about between 1 and 40 million pixels. They can change their apparent temperature over 1,000 degrees in a few milliseconds and back. Oh, and we could do that for way less money than what they spend on developing the focal planes, right? They spend billions of dollars on the focal planes. And then years later, they come to us and say, you know, we need a way to test this. And, you know, can you build like this thing that, you know, that takes thousands of, you know, or thousands of watts and does all the stuff and is bigger and more expensive and more of a pain and has all kinds of weird materials. Can you all do it for you know, a few $1 million, do you mind? So some of the challenges that come on with this is like the pixels have to support thermal gradient, like 50 degrees per micron, right? So this is where the pixel is attached to the substrate. The substrate is held typically at around 0 C, although sometimes we run cryo, we're running at 100 Kelvin. From here to here is on the order of like 20 microns, and this whole thing is over 1,000 degrees. And you have to go up and down in milliseconds. You want minimal crosstalk. That means that this pixel gets flaming hot, and you want this pixel to be at 0 C still, like right next to like 4 microns away, and you want it to be basically not change any. We have power densities of over 1 kilowatt per square centimeter. That is an enormous amount of power to dissipate. And for some of the newer things, we're looking at data rates at over 30 gigabits per second, which is really, really fast and really, really, really a lot of data. So, and we get to do all that for tens of customers worldwide. So there's not an enormous market for scene projectors. And we actually have plenty of customers worldwide that would like to buy from us that we are not allowed to sell to because they're the people that would be shooting at us someday. So there are material property challenges. That's like some of the things. New pixel designs are difficult, right? They want us to always get hotter and faster and smaller. So, and it can be very challenging because material properties at temperature are not well known. It's not like you can go to a book and say, you know, let me go find the flaming hot material that I can make a 40 micron square out of that'll get to 1,000 C and cool off and warm up and won't die. You can't Google that and get it, right? So you Google your best shot and you say, you know, I'm going to go pick this flaming hot material. And then you make your pixel and you turn it on for the first time and it goes from this to this, melted right across the top. Okay, just pixel dead. Okay. Oh, and it gets worse. Fabrication times take about a year and about $1 million. So that, 1 year, $1 million later, and this is what we got, melted pixels. Yeah, okay. Customers are not really happy with us. But they really need scene projectors, thankfully, so they give us another chance. The one saving grace for all this is these are all done with photolithography. So the marginal cost of adding a design is small. So in the 1 year that it takes you to make 1 pixel, you can make 100 pixel designs. You just got to pay somebody a few hours per pixel design to do it, and then you're done. Other challenges, pixel properties are dependent, and that can be very frustrating. So the longer legs, like you make the legs longer, it takes less power to get the pixel hot, but it also makes the response time slower. It takes longer for it to settle when it gets hot. It takes it longer for it to cool off when you're trying to go down. So you want higher temperatures, but you want fast response times, and you can't get both by changing the leg length. You think, I'll make the pixels thinner. That'll make it faster. I'll get rid of that. Yeah, that's great, except that when you make the pixels thin, they turn into potato chips when you heat them up. Right? Because you're getting this thing 1,000 degrees, and yet you're holding part of it still. So it will do some crazy things. So there's always this balance when the pixels, and there's no perfect design, and my whole job is to try and make some balance between all of these things to get something that meets the customer's needs and doesn't take, 50 kilowatts to run. So how do you do that? How do you make a new projector and don't blow up the budget and get the program canceled? So the answer is you build a bunch of pixels in parallel, make lots of pixel designs, build them on, make models based on empirical data. So this is just like what you do in the lab. You took measurements from the last set of pixels that you made, go through and take those and try and extract material properties, because nobody publishes what what some refractory metal thermal conductivity is, especially thin film thermal conductivity, at 1,000 C. You're not going to find that anywhere. So you got to make a guess and kind of extract it from your own. Guess at a bunch of design geometries, add some FEA to try and throw out the designs that you already know will be bad because they have high stress or something else. Make a range of leg lengths because you don't know what the thermal conductivity is. So you just guess. You make lots and lots of pixels, and then you test and test and test some more and keep testing until you figured out which design is the best, which one gets the temperature with the power, with the speed, and then you run that one for hours and hours and hours to make sure it's reliable, that's not going to break. The testing is the same thing you do in the lab. Voltage, current, radiance, all the same stuff we did in the lab, just like you're in a lab, because you are in a lab. Doing the same thing you are as a graduate student, all the same. It's just, you're getting paid more. Some of the system challenges, that's just the pixels and materials part. There are other challenges you got to do. How do you get the power in? 1,000 amps peak into like a space that big. You want to prevent inductive spikes. You got and the other thing you got to worry about is it's 1,000 amps peak. Like, we do not make something that you can run with 1,000 amps going through it for like an hour without blowing it up. So you need some way to prevent it, to keep it from being damaged. So you cheat, right? Use a small power supply, use some large capacitor banks, so you get the big 1,000 amp peak, but then the capacitor drains and the power supply can't support the 1,000 amps, so that when the customer does something stupid, because the customer will do something stupid, right? The customer will turn it on at max to see what happens. Yes, we've had to even do that. Oh, let's turn it on at max and blink the whole thing on and off for an hour just to see if it's stable. Oh, no. So we do things like this so that, to protect the customers from themselves and to make sure you can't break things, even if you try. You got to get the heat out. So you got to support temperatures in some cases down to 100 Kelvin. This can actually be really challenging because you're doing massive temperature changes. And so there's a thermomechanical challenge. You have to do a lot of work with the mechanical engineers to figure this out. We end up using custom high flow chiller or coolers with lots of low thermal conductivity materials. Then there's a challenge in getting the data in, right? You got data rates and analog settling times that the double E's need to worry about. And mechanically, you're trying to put sometimes 250 wires into something that's got maybe an inch or two across that for you to put all this data into. It is not easy. There is lots and lots and lots of challenges involved. So And to do this, we end up with custom designed electronics and cables and these giant co-fired ceramic things that chip carriers that are made in industry. And then lastly, it's once you do all that, how do you make the uniform, the output in image uniform? So these things are not perfect, and we don't make tons of them like the TVs, you know, where they make the TV and everything's all exactly the same. You know, we make, if we're lucky, tens of these a year, and so they're never just right. And so, and then even figuring out how to make them uniform is difficult because you want to look at this thing with a camera, but then you got to make the camera uniform some other way by looking, it's not perfect either, right? You got to go figure that out. You can't get one pixel to one pixel, right? Because it's not, because you can never image exactly the pixel onto one camera pixel because of optics and other things. So it's just a huge pain. And if you want to really try and make it perfect, you'd measure one pixel at a time. If you do that over the range of temperatures, it takes you like a year to do one non-uniformity correction on one scene projector, and nobody's going to stand for that. So you end up with some challenges with this electrical and software to figure out how to collect the data, and then all that data has to, all that non-uniformity correction has to be provided in real time because you don't calculate the scenarios in advance because it's hardware in the loop. So you can't know what the missile is going to do in advance. So the missile does something, it goes through the simulation with almost, you know, with milliseconds or less, with less than a frame of latency. So just, you want to have a microsecond times latency, you need to do the non-uniformity corrections on the data as it's coming through and correct it. So you end up taking something that looks like this to something that looks like that. Right? Way better in non-uniformity. We start with like 20%, and nowadays we can get uniformity. You can't see it in here, but our uniformities are typically for sort of the mid-range of radiance is typically less than 1%, 0.5% or so or better. So, and how do we do that? 15 years of incremental improvements. You go through, and we started off and we were like struggling to hit 3. And then you figure out another way, you make it a little better. It goes down to 2. You make it a little better and goes down to 1. Now we're down to like sub 0.5%. So, but it's just work. And it's just little things, incremental improvements. Go through and come up with some new way of doing non-uniformity correction. You go through and you do an IR&D, you figure out what to do, you run the test, and you make it work. So now I'll talk a little bit about my take on being a physicist in industry. So, number one, don't limit yourself to jobs that just say physicist. There's not that many out there. And actually, the vast majority of products out there, things that people make, are not just one thing. It's an integrated mix of multiple disciplines. There's electrical engineering, there's mechanical engineering, there's software. All these things have to come together to make something, to make your phone, to make your car, to make your whatever. Like all these things, there are lots of people involved. And somebody, when you make one of these products, there is somebody that serves as the system engineer, the guy that sits and talks to everybody, that talks to all the other engineers and says, he knows enough about software to talk about software. She knows enough about mechanical engineering to be able to talk to the mechanical engineers, or to be able to talk to the double E's, and enough to kind of know what they're saying. You don't need to know everything. You don't need to know how to program in VHDL. You don't need to know how to do finite element analysis in mechanical engineering or anything like that, but you need to know enough about it to be able to talk intelligently and to make a decision, because somebody has to sit in the middle and figure out when to make trades, because sooner or later the ME guy is going to run up to a roadblock and he's not going to be able to fix it without spending piles of money. And the system engineer can say, you know, that's almost where we need to be. And we have a little bit of slack over here in double E or in software that I can fix it. So you don't need to go and make this huge expensive change. So you need somebody in the middle, and the physicist is uniquely qualified to be that person. So as for my take on my part as being a physicist in industry, I can say my career to date has been very, very fulfilling. I've had the privilege to work with some fantastic scientists and engineers. I've worked with people from NASA, from Air Force Research Lab, Naval Research Lab, night vision labs, Johns Hopkins, Applied Physics Lab, MIT, Lockheed, FLIR, many others, many small companies that you guys have never heard of. I've worked for all these people and they are fantastic, truly fantastic engineers and other scientists that I've worked with. I've interacted with customers and vendors all over the world, and I've traveled all over the world to support sales and system deliveries and things like that. So it's been a really, really wonderful career. I've attended conferences, given technical papers, got invited to this thing. So, and I can say there's plenty of work out there for people like us to do. There are plenty of problems to solve. The main trick is to find the right place. Okay. For me, that right place was Santa Barbara Infrared. Okay. It's a really nice place. It's a fairly small company. I get to interact with lots of people. I get to do more than just one thing. So it's been a very good fit for me. For somebody else, it may be a larger organization like the Lockheeds or the FLIRs or something else like that. Working with them, I can tell you that, yeah, I would not fit in well there. But Santa Barbara Infrared is actually, we employ a lot of slightly weird people. And so I tend to fit good there. And so the trick for you guys, if you choose to go in industry, is to find that place that's a good fit. And you know, if it's not a good fit, go somewhere else or go do something else, right? Don't fight the job. I can say that, like, don't fight the job. If the job changed, like for me, Spectier was wonderful. Oh my goodness, I had so much fun in that job. Management changed and I wasn't going to get to do what I want to do anymore. Okay, I left and I'm happy that I did. Very happy that I did. I'm very satisfied with my job at SBIR. I don't get to fly anymore. Okay, so I don't get to do the one thing, but I'm still problem solving and doing other things, and I would not be able to do that if I was still working at Spectier. So a little more for you guys, how to get the job and keep the job, right? For those of you who actually aren't going to go into academia. Communication is like the most important thing. You have to be able to understand and communicate what you're doing and how it relates to the big picture of everything else. You need to be able to tell somebody what the overall goal of what this thing you're trying to do or build is and what your part in it is and how it relates to everything else. I can tell you, I interview every technical person that comes into Santa Barbara Infrared. I do not ask them any technical questions whatsoever. I leave that to the software engineers, the mechanical engineers, the electrical engineers that go and talk to them. I leave it to the other system engineers that want to talk to the system engineers. I let them go and ask them to solve problems on the chalkboard or something else like that to show they technically understand. I ask them, go tell me something you did. And when they start explaining it to them, I ask them, what was the point? Why did you do this? How does this fit with the overall thing? What did you do? How did you solve a problem? I ask them questions like that to make sure that they can communicate with me to say, they understand their part in the bigger picture. Because if they don't, they can't communicate with the other engineers, then we don't have a place for them because you have to be able to interact with other people. If you can't interact with other people, there may be another job for you somewhere else, but not at SBIR. So learn to respectfully disagree. Okay, that means when somebody says something with which you don't agree, you don't say, ha, and then insult their intelligence. Yes, I had Woodard for thermodynamics. So yes, I know all about it. Yeah, don't do that. Okay. Even when they just made some snide remark about being a PhD, where they come to you and say, we need you to solve this problem. Oh, and I know you're going to ask for more data. So just tell me what you want me to do now. Freaking PhD. I know you're going to ask. Yeah. Okay. Yes, I'm going to ask for more data. And here's the data that you haven't collected yet. Be nice and polite, especially to the president. And the last thing is your job will be difficult sometimes. When it is, rejoice. Because if your job was easy, somebody else would do it for less money. So you be happy when your job's a pain, because that means that they need somebody smart and dedicated like you to do it. So suck it up. It's a pain. Yes, excellent. That's why they pay. So just in case you guys think that I'm some sort of physicist unicorn, I am not. These are some other people that either have worked or still work at SBIR. This is Tom Danielson. He got his PhD in high energy physics. He was a postdoc at UCSB, came to work for us, worked on worked at the LHC, basically worked on the LHC. So he was like a high energy theorist, came to work for us, now hired in as system engineer. He's now basically has my old job as a system engineering manager. There's Dr. Camlet. Nah, he's double E, almost a physicist. With double E ellipsometry, also hired in as a system engineer and is now our quality manager. There's Dr. Adams, PhD in physics. He's like, does my job for IRC. IR Cameras is one of our subsidiaries. There's Jay James, who was also a PhD in physics. When I started, he was the sales director at SBR. Now he's like a big shot VP at FLIR. For those of you who aren't getting a PhD, there's Mr. Franks, right? He was hired with a bachelor's degree in physics out of UCSB. He was hired as an SE. He's the guy that I talked about earlier that said he wanted to be a manager. Nice freaking VP. He's like my boss's boss. So, bachelor's in physics, now VP of the company. And there are others, Chris Holmes, Madison, Sullivan Hames, and Jake Singer. These are all people that had bachelor's degrees in physics that used to work for SBR, have now moved on, but moved on because they all moved out of Santa Barbara for whatever choices in their lifestyle. Mr. Holmes wanted to raise horses, which is very expensive. Miss Sullivan Hames, her partner, moved to Seattle, so she went to join him. And Mr. Singer left to study medical physics. He went back to school to get a master's. But they're all doing well and have had successful careers. And the last thing is the life part. Right? So your professional career will almost certainly be longer than your academic career, unless you go into academia. So, like, try to integrate your career into your life. Don't try to integrate your life into your career. Okay? So, I will tell you that some parts of it will stink. Right? It really, like, there are days when things are not fantastic because it's a job and they're paying you because it's not fun all the time. Yeah, you'll have to do annual performance reviews. Ugh, it's like the worst thing ever. Vendors will fail to meet specs. Another terrible thing, which ruins your program and make them come to, yes, to come and screw up your schedules and your costs and everything else. You may have to spend weeks and weeks doing requirements definition, which is really boring and will drive you crazy. Or 4 different programs will have something break at the same time, and the 4 different program managers that run those programs will come to you every day to tell you that theirs is the most important and that needs to be solved right now. And so so when that happens, find something to do that's not work related, that's productive. Now, find something to do that's not work related that's productive or useful. This is not like, watching Mr. Beast mash up cars on YouTube, right? Go find something that's fulfilling to do. Okay? You're one way or another, when you get a job, like your job is to be creative in some way, right? You're going to go out there. People are asking you to go out there and think and to figure stuff out and to do things. They're not asking you to just push a button repeatedly. If they wanted that, they'll go hire somebody who got a degree in business to go do that, right? They're not going to hire the physicist to go do these things. So you need some creative outlet. Find a way, a different path to fulfillment that's productive, that's not related to your job. For me, that's woodworking. For some of those other people that I talked about before, Dr. Danielson, he teaches improv. Dr. Camlet, he is heavily involved in the Boy Scouts. There are things that you can do, that you can go and Arn, Dr. Adams, he works with the local robotics teams in high school. There are things that you can do where you can, on the weeks where you've had nothing but bad things happen, you can go home or go do something else and be productive and be fulfilled. Because if you're not, if you go through, sometimes that week is like, not a week, it's a month or 2 months, and it's miserable. And having some way to feel fulfilled will really help your peace of mind and make you like a happier person and help you with your life. So just remember, and the last is, there is more to life. Like, take some time to enjoy it. My family, right? The youngin' back there, my wife, my other son, my various nieces and nephews and their kids. Have a life, enjoy it. So thank you very much. If you got questions, I'll take them. If you want to contact me, you can contact me on my Gmail. And thanks for your attention. Yeah. So it depends. SBIR is not too bad. Actually, while I was in aerospace, I did 2 summers as an intern at Pratt and Whitney. They make jet engines, and it was much worse there. And yeah, like I said, I could not stand to work for Raytheon or FLIR or Lockheed. They would drive me crazy. Yeah, one example for just how insane those people are. We had a meeting several years ago. We had some people from Lockheed, from one of our customers. We had a meeting to talk about a new design. The first 20 minutes they spent defining the word "not" in their specification. This is this, not this, right? That 20 minutes. Okay, they went through and this woman got on and she talked about all the and don't get me wrong, she was a lovely person. She was a pleasure to work with. But oh my goodness, she went through every possible explanation of what she meant by "not." And we were like about 10 or 12 minutes into the meeting, and somebody else came on the line that was late, and she went over it all over again. And I was like, it's like an hour-long meeting. We spent 20 minutes talking about one word. I was ready to shoot myself. It was like this. Oh my goodness, if I have to do this with every customer, I'm going to quit. So thankfully, most of our customers are not like that. And SBIR, the smaller companies, you'll find the smaller companies have less of that sort of stuff than the larger ones. So anybody else? No?
There are questions on Zoom. If you'd
Ah.
like to-
Oh. Any questions from the Zoom people? Ah, Pradeep's here. Ah, Dr. Kumar. Well, what do you know? Hey, Dr. Kumar.
Joe,
I can't hear him, but it's still good to see you. I can, sorry, my hearing's not great. Why did I choose?
After
Yeah. Oh, because I couldn't, so I was going to go back to school, and I thought I would go back to school and get a PhD in aerospace. But when all the defense cuts got done and all the funding from the companies to the school also got cut. So if I wanted to come get a PhD in aerospace, I had to pay everything myself. I would have been paying like my tuition, my housing, my everything, and I didn't have that much money. So, okay. So actually it's kind of funny. I came and talked to Professor Field. He was the he was the graduate advisor at the time. I said, hey, I got this problem. I'm thinking about going I want to get an advanced degree, and I studied in aerospace. And he starts laughing. He's like, well, I went into aerospace engineering back in the '60s because of the space program. He said, and I graduated right when they went to the moon, and they cut all the funding. So he said, I switched to astrophysics. So the same thing, right? The same thing that happened to him that happened to me. He said, okay, funding from physics is much lower than aerospace on average, but it's constant. If you can get into the department, you can pass the qualifying exams and if you get accepted in the department, pass your qualifying exams, we'll figure out a way to get you out. Figure out a way, don't do anything stupid, but we'll find a way to fund you and find a way to get you through your degree. And they did. So 1 year of TA, or 1 semester, sorry, of being a teacher's assistant, and the rest of it I was either funded by the government under a I can't remember the word now. What's that? There's basically a National Science Foundation or national, I don't remember if it was NSF or National Education, but a grant, and then for 1 year, and then one semester as a TA, and then I was a research assistant for the rest of my time. So totally true to his word. Yep. Anything else? Yeah. Yep. Yep. So it really is just talk to people. And like the place to talk to people is at conferences and things like that. Go and talk to the, especially if you see people like if you're in academia, it's kind of easy, right? You're going to go to the conference, or going to people the conference paper, give them papers at the conference. If it's the field you're already in and you're interested, that's pretty simple. If you're trying to get into industry, it's a little bit more challenging. But there are still things out there where you can go and talk to, there are still things like SBIE, okay, it's the optical engineers, and okay, not the, the Society of Physicists, but still they do stuff and they do research and things like that. And you can go to one of their conferences, or at least look on their papers and see if there's something you're interested in. If you find things that those people are doing, you can reach out and ask them questions about their papers or other things like that and talk to them. Or especially like for here now, the Defense and Security, SBA Defense and Security happens in Orlando once every 3 years. And so it used to be every year. It was really easy. It was great for me. I came every year. I get to go home and visit my parents, and it's all paid for by the company. But these days it's like once every 3 years. But still, it's not that far away. Drive down. They'll give you a guest pass to go in and visit the you can get a guest pass to go and visit all the vendors. That's free. And it's not terribly expensive if you want to actually go and sit on some of the talks, but all the talks you can go through and read the abstracts and stuff and see if there's anything you're interested in. If there is, almost all the vendors are giving the talks. So you can go and read the abstracts. You're interested, go to that company's booth, because almost all of them have a booth somewhere, and then go and talk to them at their booth and don't have to pay to get in. So yeah. Anything else? No more?
Well, there's nothing else, I guess.
Right.
Thank the speaker again.
Thank you very much. Thank you for inviting me.
Oh, we have